Welcome to the video. Today we are going to extend from our previous videos on probability theory in coin tosses. Let me ask you a question. Suppose there is a population and there is a disease ongoing, and there is a test invented to test that disease, and it has 99% accuracy. Then, if there is a person who is tested positive, what is the probability that he has that disease? Can you think about it? Do you think it is 99%? Because the test has 99% accuracy and the person is positive. Okay. Let me ask you another question. Because we are in coin toss zone or domain. Suppose we flip two coins, and one coin, I tell you that we have one head. What is the probability that the other coin will also be a head? Will it be 50%? Okay. So the answer to both are no. This is where conditional probability comes in. Because when I gives you the condition, it actually changes the game. It reduces the sample space. Again, let me repeat. A condition given reduces the sample space. Okay? Let's ponder on it a little bit, and then let's look at how a coin toss, my question on the coin toss, will finally look like on a decision tree. Okay? So let's say this is the first toss, and these are two outcomes. One is head and one is tail. Then this is the second toss. It will have head and it will have tail. Similarly, it will have head and it will have tail. Okay? Now the question that I asked was, we are given that there is a head. Okay? So let's say if I had asked a different question. Let's say if I had said that the first is head. So this one, if this is head, then what is the probability that the other coin is also head? The result is also head. So it would be 50-50 because we know this. So we are in this umbrella now. So it will be either this or this. So half-half. So this will be 50%. But what is the question saying? The question is saying there is at least one head. Okay. So we see that there is a head here, but we cannot ignore the point that there is a head here also. Correct? So if you think, so the two tosses will look like head head, head tail, tail head, and tail tail. Okay. So how many of these at least has one head? 1, 2, and 3. This one is ignored. So when I give you a condition, it actually eliminated this term. So it reduced our sample space. Earlier, the sample space was HH, HT, TH, and TT. So then when I give you the condition, it actually reduced or I eliminated this, right? So now we have only 3. Okay, now in these 3, I'm telling you that there is at least one head. So what is the probability of getting the another head? So meaning we have to find the two heads. So there are two heads, right? So two heads is only 1, and then at least one head is 3. So the probability is 1 by 3. It is not 1 by 2. Okay? Clear from here? This is how a conditional probability emerges. Now this is a tree diagram that shows you visually. I'll also go over the equation. But let me come back to my first question on disease. Let's try to understand that also. So what I said is, there is a population which has either disease or no disease. So disease or no disease. Okay. Now what I said is, there is a test. So it will either be positive or negative. Here also it will be either positive or negative. Now the information that I gave you was that the accuracy of the test is 99%. So the person with disease will have a positive result 99% of the time and a negative result 1% of the time. Correct? A person without disease will test positive 1% of the time and negative 99% of the time. Okay. Now, when we ask this question that what is the probability, now I will show you how this is written. Suppose A and B are events. A is the event of disease, okay, yes, and B is the event of positive. So the question that I am asking is P of A given B. So this is how it is generally denoted, that whatever is the second after that slash is the given condition, and this is what we have to derive. Okay. So what is given to us? We are given that it is positive. Positive is here, positive is here. So there are two positives here. Okay. But how many people have this disease or how many people do not have this disease? What is this 99% of? What is this 1% of? They are a percentage of how many people have this disease. And this is 1% of how many people have this disease or they were tested. Correct? So this is kind of a population distribution with disease and not with disease. And then a sample of that disease has been taken, and a sample of that no disease has been taken and then sampled here. But the actual value of how many people have disease and not disease in this population is not given. So that is the thing that is omitted. If B is given, that B basically corresponds to this is B and this is B, and A is this. So we are asked, if B is given, what is A? Correct? So in B, it is not just this B, it is this B also. So we have to take into account both. Now let's say the population is 10,000. Out of that, only 1% people, it's a rare disease, 1%, it's also not very rare, 1% is a lot. So 1% population has this disease. So how much is 1% of 10,000? 100. And no disease will be 9,900. Okay. Now we know that the probability of no is 1 here, because 1% of 100 is 1, and then this one will be 99. So 99 people will have the disease if they are tested positive, and 1% will not have the disease if they are tested. Here it will be the other thing. So 99 people will be positive, because even there is a 1% failure chance, and the rest of them, which is 9801, if I'm not wrong. Okay, so this is the total number of people who will test negative. So this is 99% of 9,900. So now what we have to see is the total given is P, then we have to find A. So now our sample space is not, this is whole 10,000. So our sample space is not 10,000. Now it is only this and this. So 99 plus 99 is 198. So our sample space is reduced. And then we want how many of them will have disease. So all these 99 actually has the disease. So we put 99 here. So this will become 1 by 2 or 50%. What? Right? So there's a 50% chance. It's not 99% chance. So there is an equally likely probability that he may or may not, even if he's tested positive. I think a lot of times when we go to the doctor to ask for, and there is a positive report, he will always refer us to the next steps. That you try to do this thing also to confirm. He's never sure because a lot of times the diseases are rare, and then the test accuracy is not 100%. So that is why conditional probability is very heavily used in this medical field. Okay. I think what we understand from here is pretty simple, or I hope clear. Then let's look at the formula now. The formula for a conditional probability is P of A given B is given as P of A intersection B divided by probability of B. Now this might look a little difficult to remember at first, but let's understand what this actually says. So as I said, when B is given, our sample space is already reduced. So let's say let me draw a Venn diagram. So this is probability of having an A, this is probability of event B. So what we are saying is, we are already given that it is all B, right? B is already given. So you see, now we don't have to worry about this part of A, which is not in B. Okay. Now they're saying that we have to find A when B is given. So A is this part only. So this part is actually P of A intersection B. So this is what we are putting here. And B is everything that is there, we have put here. So another great mathematician, Bayes, came up with a theory based on, he derived it from this formula. So what he said is, it is called actually Bayes Theorem. He said P of A given B is the same as P of B given A multiplied by P of A divided by probability of P. Okay. So this looks like a little complex again, but let's try to understand. It's very simple actually. So let's say if you multiply this with PB, right? This side. So PB multiplied by P of A given B is equal to P of A intersection B. Now the same thing can be written as P of B intersection A, isn't it? Because this is an intersection of two. Either you say A and B, or you say B and A, both are same. So what this does is, it will, and then you can basically reverse this. You can just replace A with B and B with A. So here this will become PA multiplied by P of B given A. Okay, we have just flipped this around, replaced A with B and B with A. So the same thing is written here, that if you see this P of A of B is here, P of A into PB over A is here, B given A is here, and then PB again goes in the denominator here. So sometimes what happens is, we know a probability the other way. That makes it easier to calculate the original probability for a condition. So what this says is, given this condition, what is the probability of this happening? you can know this in terms of, given the result, what is the probability of B happening? The condition, what is the probability of condition happening given the result? And then there are some factors that you need to multiply it with. Okay, so if you are able to identify this, you can calculate this. So this is kind of a role reversal, knowledge. So that is Bayes theorem. It is applicable in a lot of places. All these conditional probability things are applicable in a lot of places. Like I just said, that in medical field it is applicable. All those places where you have to actually make a decision. So all those decisions will be influenced by the given condition. So it will be used in, this whole thing is used in many different places. Let me solve some of the questions in my next videos, so that that will make it more intuitive and clear. You can keep on giving me comments on whether you want to see more of certain kind of clarification or certain topic for me to cover. But I'll keep on making videos. Enjoy it. Keep learning, keep watching, and hope you like this video.